fractions of quadratic irrationals.
Is it working? Yeah, okay. It's a great pleasure to visit once more this institute and to be at the conference dedicated to David, long-time friend. But the building is completely new for me. I have some difficulties to recognize it, but it seems it's the same institution, I hope. Well, I had some doubts choosing the subject because it's so far from modern mathematics. It's many millenarios years old, so that most modern mathematicians do not know what is it a continuous fraction. So the simplest example, that is a series of natural numbers, or even maybe zero also included, so that's non-negative, or as they call them, positive in Paris. Natural. That's French natural numbers. You know, French natural numbers start from zero. Yeah. That's a continuous fraction. It might be finite, it might be infinite. If it is finite, it's a rational number. If it is infinite, it's the limit of rational numbers you obtain cutting it somewhere. Well, now I shall start from a celebrated and very strange theorem by Lagrange, namely, this continuous fraction is periodic if and only if the number is a quadratic irrational number. If there is a quadratic equation verified by it. It's a necessary and sufficient condition. However, some of the roots of such equation might be rational numbers too. Then it is, I shall call it periodic with period zero. Length of period zero, because it is finite. Yeah. And then the periodicity means that ak plus t equals ak, starting from some k. And this number t is called the length of the period. T is chosen for time, because I am thinking always on dynamical system for which t is a time. There is a dynamical system related to this object. It has been discovered by Gauss, who was unaware of definitions. And so he discovered the main theorem, but he was unaware of its formulation. He discovered the result, but neither the proof nor the formulation. The formula is by Gauss. It's even today called the Gauss formula, but it's a very strange object. Who is the real discoverer of the Gauss formula is a difficult problem, because, you know, that's the following problem. Sometimes those numbers are very small. The golden ratio is a quadratic irrational number, and hence it is periodic, the continuous fraction of it. But this continuous fraction is very simple, because, you know, square root from 5 is 2 with 2, and so difference is 0.6. Yeah, so it is 1 divided by something which is more than 1. That's the definition of the golden ratio, in fact. If you take the definition of the golden ratio, it's a postcard, such if you cut a square, the rest is the same form. Yeah, it means that all those factors are 1. It's a periodic with a period 1 and with period element, which is 1. Then there is a following theorem due to someone earlier than Archimedes, maybe some millenary earlier. If sum of these numbers is very large, and if you cut just before, you get immediately an excellent approximation to the irrational number represented by the fraction. So to get the best approximations of the fraction, you have just to develop your irrational number as a continued fraction, find the good place where the next denominator is large and cut it there. And for instance, the celebrated approximation of the Archimedes number, what is the English of it? Pi or P? Pi? That's strange for me, but pi is eatable.
Many jokes have been made of this.
Yeah. So, you know, 22 divided by 7 is the first continuous fraction, but there is a better one. You write the decimals. Twice 1, twice 3, and twice 5. You cut it. And this is an approximation with up to 1 millionth of this celebrated number. It's the best approximation, which is better than that of Archimedes. Huh?
113 in the denominator?
Of course. Thank you. Thank you. That's, you know, that's a special kind of Arnold lectures. Giving lectures in Moscow University, I had this habit from the very beginning. All the minus should be plus, all the 2 in the denominator should be in the numerator. And then immediately they start to understand. If you never do it, they never understand. They learn it by heart, they answer the examination without understanding. But if you make such mistakes, it's okay. Okay, so be aware for the continuing of the lecture. Okay, anyway, one is very common when you have a lot of numbers. And you know, they are very important in celestial mechanics because you have the Keplerian motion of planets. And, oh, sorry, usually you are at the north part. And then the periods ratio might be a rational number. If it is not, it might be approximated by a rational number. And it's called the resonance. And this resonance produces a perturbation. This is the sun, but the perturbation of one planet by the attraction of the other is much higher when there is a resonance. When there is no resonance, the perturbative force is directed toward different direction, and so the averaging make a 0. But if it not, there is such a phenomenon which is called secular perturbations. For instance, if you have the Saturn and Jupiter, are the English words? It's American words, it's okay? Saturn, Jupiter, you understand. Yeah, and then you have the velocities. Well, I know it by the astronomical units. They think on the seconds of arc in a day. And so it's very close to the resonance. What is it? 5 omega, no, it should be, no, maybe I give some, I think it was 2 to 3. 2 to 5 really? No, this here it is 2 to 5. But in the reality, I think it was 2 to 3. And so perhaps perhaps numbers are, well, anyway, I have forgotten the real numbers. I was in this celestial mechanics 40 years ago, I was aware, but today I have forgotten. Anyway, there is some resonance. I think it is a resonance of order 2 to 3, maybe 3 to 5. I have forgotten the exact. But anyway, it produces a large perturbation, secular perturbation, which in fact is periodical. But the period is between 8 and 9 hundredths of years. And because of that, during 400 of years, the distance is growing. And so there is an impression that Saturn wills to destroy the orbits of Jupiter, which will come to infinity. However, the next 4 centuries, it will return. And since 4th century is a long time for astronomers, there were very, very serious theological discussions what will happen to the solar system. However, you know, this fact is making very important continued fractions, because to know what will happen to the solar system, you have to compare the angular velocities of many periodical motions which exist in solar system, and to see what are the continuous fractions. Where if there are very bad good approximations, it means very bad for the astronomer's case when you have a very large A. Then you have resonance, and then it's dangerous to the collisions of planets. Because of that, Poincaré have discussed it in his Méthode nouvelle de la mécanique céleste, and he proclaimed that you have to make tables of continued fractions for all the ratios in the solar system. And a dozen of important resonances have been discovered. Well, for instance, there is a resonance between the satellite of Jupiter and so on. However, later the students of Poincaré, like Newcomb, have published it in the Compte rendu de l'Académie des Sciences Paris, they have published the lists showing that the statistics observed in the solar system, practically, is that of Gauss. Gauss have computed what is the proportion of ones for a random number continuous fraction. What is the fraction number proportion of elements A equal to 2, and so on and so on. In fact, he was unable to prove it because it's wrong. Because, in fact, rational numbers are very different, and periodical numbers are not like the random numbers, and so on. So, to prove this theorem, you need to say it is true for almost all real numbers, not for all real numbers. Almost all. There are exceptions. Those exceptions form, of course, an everywhere dense set. But it is of Lebesgue measure 0. But unfortunately, Lebesgue was not there still. So at that time, it was impossible for Gauss even to formulate the theorem, because the theorem has exceptions. It's not a real theorem in sense of Bourbaki. It's a theorem with exceptional set of measure 0. And then later, at the beginning of the 20th century, there was a 400 pages long paper in the Swedish journal by the mathematician who later becomes the president of Swedish Academy of Science, Wieman. And Wieman had written something on a probability problem arising from continuous fractions. That's the title of his paper, which is 400 pages long. I have never met any mathematician who was able to understand it. I do not know whether it is correct. I do not know whether he had formulated or proved the Gauss theorem. However, 28 years later, there was a Russian mathematician, very great mathematician, Kuzmin, who had proved the Gauss theorem. Is published it in 1928. It's very strange. There is a very nice description of this proof in the book Continued Fraction by Hinchen. But this is the deduction from the dynamical system theory. The dynamical system of Gauss is the following dynamical system. You have a number x, which is in the interval 0, 1, and you send it to 1 over x. Of course, 1 over x is not in this interval. So to put it inside this interval, you have to subtract its integer part. This fractional part of 1 over x is indeed a number between 0 and 1. Theorem by Gauss, I think. This mapping preserves the measure. The Lebesgue measure is preserved by this Gauss mapping. It's a very strange theorem because this mapping is not a bijection. It's not one-to-one. The preservation of the measure should be defined correctly. The correct definition of the measure preservation, you may think that it is that the image of a set have the same measure as the set itself. Wrong. It doesn't work. You have to distinguish by the main ideas of main mathematicians between covariant and contravariant objects. And measures are going back. They are like cohomology. And so you have to consider a measurable set in the image and the pre-image. And the complete pre-image measure is equal. And this is a theorem. And this is a very, very nice theorem on telescopical summation of series. Anyway, Gauss have found the invariant measure of this. It's a measure with a nice density, and I leave you the pleasure to discover it. And Kuzmin have proved that the probability formula is the following formula given by Gauss. Oh, I had written it somewhere. Strangely, it should be somewhere here. Where is the Gauss formula? Sorry. Very strange. The important part is that it is declining with the integer as 1 divided by the square of this integer. So the sum is convergent. And the coefficient is also calculated explicitly. Anyway, the delicate point was that this proof of this Gauss-Kuzmin theorem is based on the ergodic theorem theory of dynamical system by Birkhoff, which have been proved 5 years later. It seems to me that Kuzmin was aware of this theorem, maybe not for all the cases, but for the case he needed. His proof was much longer than the Hinchen version of it, reducing it to Birkhoff. But I think that the Birkhoff theorem was discovered by Birkhoff later than the Kuzmin proof of it. Anyway, now I shall discuss the following problem. We know the probabilities. About 50% of elements are 1, according to this measure. About 15% are 2, and so on and so on. All numbers, of course, occur, but with declining probabilities. However, if you have a periodic, first, I have formulated about 20 years ago the following 2 conjectures, which seems to me such a challenge of mathematics and astronomy, of those problems to mathematicians. instead of the random real numbers, consider rational numbers. Then rational numbers can be ordered, you know, say u divided by v, and you have a continuous fraction for each of them. Then you take all the numbers where u and v are not too large. There is a finite set of them. And you count the number of a equal to 1 in the corresponding developments. And you divide it by everything. And then you take the limit where r is infinite. Conjecture. The limit would be the same as the average for all the Lebesgue measure studied real numbers. Yeah, I had difficulties. I have formulated this to my students, even to my student who is now at San Francisco. No result. They were able to check it on the computer till this radius r till, say, 1,000. It's okay. But the limit, it's rather difficult. However, 5 years ago, my other students at Vladivostok, you know, the closest mathematical center of Russia to San Francisco, they arrived to prove it. However, they also have proved another conjecture of Arnold. At the same time, I have formulated it. Consider the periodic case. In the periodic case, say for such equations, then if the coefficients integers r, p, and q are fixed, then there is a fixed period. And this period contains some numbers, 1, 2, and so on.
Say the conjecture again.
If you fix x, a quadratic irrational number, its continued fraction is periodic. In this period, you have the numbers ak, you have the numbers ak0, ak0 plus 1, ak0 plus t minus 1, t numbers forming a period. Taking the periods for all the quadratic irrationals for which the coefficients are not too large, you count the number of elements a equal to 1, to 2, and so on, divide by the totality, and then you get the average. And then the Arnold conjecture formulated 20 years ago have been that it is also the Gauss-Kuzmin statistics. And today it is also proved. 2 years ago, the Bykovsky and his students, Avdeyev, Romanov, and others at Vladivostok has proved it is too correct. Both are correct. Today, however, I shall report other results. Namely, classically, we know the statistics of the elements. And we know that it is even true for the periodic case of quadratic irrational numbers. However, the period itself is also variable. Question: how large is the period? Similar question. For rational numbers, if you have the fraction u divided by v, you have a finite set of elements, and it also have some length, the continuous fraction. It's dependent on u and v. What is this function? T of uv. Period, length. Yeah. And I shall now report you the results. I have started as a physicist, not as a mathematician. I don't consider proofs as an important part of science. That's, it's written by Turing. You know, in the book by Turing, whether the machine can think, it's written. that there is a mistake thinking that science is progressing by the logical deduction of one sentence from the other one. It's completely wrong. The progress of the science, according to Turing, is starting by the experiments. Then you can guess something, looking at the experiments. And then where you guess it correctly, then at the end, some centuries later, someone maybe would be able to prove something, or maybe not. You know, a typical example is the celebrated statistics of the primes. Who is the author? It's written in all the books, even I think you perhaps are mentioning the author being Adamar and Vallée-Poussin. Theorem, no, well, not you. Other. Number theories, not David, not David. Okay, Adamar and Vallée-Poussin. Adamar and Vallée-Poussin are the result. The distance between the neighboring prime numbers at the neighborhood of the number n is growing when n is growing in the mean like logarithm natural of n. That's the result. Who is the author of this result? Story. Legendre. Well, I think Legendre of the Legendre transformation and of many other domains in physics have studied this problem first. He have computed the list of prime numbers till 1 million. He observed those numbers and he derived this formula. However, in the Legendre version, it was C log n with a constant. And by his experiments, he computed this constant. And the value of the constant C in Legendre was the next mathematician starting to study this problem have been Chebyshev in Russia. Chebyshev has proved that, in fact, this mean distance is in between A log n and B log n. However, the ratio B divided by A was in his studies about 10. He liked the constant C of Legendre. And the next theorem by Chebyshev was, if the asymptotics do exist with some coefficient C, there is only one possible value for these coefficients, namely C equal 1. C is equals 1 provided that the oscillations are disappearing when n become large. He was unable to prove it. Then Adamar has proved the existence theorem. The limit exists. The Chebyshev asymptotics do exist. And now he is considered by all the mathematicians of the world as the real discoverer. For me, he have discovered almost nothing, just the theological fact, existence. Existence of the limit, that's all. He have neither discovered the behavior nor computed the constant. It have been done by Legendre and Chebyshev, and who was never mentioned in the stories of mathematics. Now, I will today represent you the Legendre type work. I am proving nothing. No, of course I have proved, of course I have proved, making those experiments, I have observed some thousands of observations. Among them, I have rejected some hundreds by further experiments. Next, the rest have been formulated as conjectures. And from those conjectures, about 10% are now proved. However, those proofs are much less interesting than the conjectures and then the remaining part. And that's those conjectures and this remaining part that I wish to explain now. Okay? Okay. Now I start mathematics. First, I had considered the following series of experiments. First, x squared plus px plus q equals 0 with integer coefficients p and q is some series of quadratic rational numbers. And I am interested in those numbers. Second, x equals square root of u divided by v, where u and v are natural numbers. This is another series, also with two parameters. We have the second two-parametric series. And then the third series, psi equal u divided by v, are rational numbers. And now I shall discuss some properties of these statistics for the continued fractions of those. In the first two cases, they are periodic, and in the last case, finite. Still, the statistics is an interesting thing. The main object I shall discuss is the length of the period in the first case, also in the second case, and the length of the fraction in the last case. The length of the fraction will be defined by the following way. It's for a finite fraction. There are some sign plus in the fraction. I count them. It's important not to calculate the number of those denominators, not to find the number of ones, not to calculate the number of fractions, just of pluses. Why is it important? Well, that's a small remark. It is equal to L of VU. It's symmetric. It's rather strange. Say, example, let's calculate L of 1311. 13 divided by 11 equals 1 plus 1 divided by, it's 2 divided by 11, 11 by 2, 5 plus 1 divided by 2. It's 2. Now, the length of the continuous fraction of 11, 13. 11 divided by 13 is, of course, 1 divided by the preceding thing. And hence it is also 2. If you count pluses and not fractions, it's okay. In other cases, the symmetry is lost. Well, in any way, the problem, what is the asymptotics of L? What is the asymptotics of T in those examples? First thing I have made, I have computed them. To compute them was very difficult. How to compute a continuous fraction development of a given number, even if it is square root of something? Of course, you can calculate the decimals of this number and then put in the computer the standard program, division, and so on and so on. It never works. Reason. When the continued fraction is long, a very small mistake in the initial number is growing immediately because of the entropy of this Gauss dynamical system. It's because, you know, here this derivative is large. This mapping have the graph like that. It's in that's if you take a segment and you take the image of it, it's much longer. The derivative is very large. Derivative of 1 divided by x is very large, so it's a very large. No, well, sorry. One of the x goes in the other direction. It's like that. The same, but I have to the axis X is here. This is the direction of the axis was wrong in the preceding picture. Okay, now, because of that, if the continuous fraction is, say, of length 10 or something like that, then you need to know 200 of decimals of the initial number to calculate it. And this is even for good computers, you know. After a few, I need, in fact, continuous fractions which are periodic with period of lengths of 1000. I have used them. I shall show you that. So I have invented some methods, but I have no time for this computerized mathematics explanation, how to compute those. I have computed them. I have computed them for, well, example. We show this equation, x squared plus x minus 60 is 0. Try to do it using a computer to find the continuous fraction. It's impossible. However, I am able to do it. And this is the result. T of 1 minus 60 is 19, the length of the period. And the period is like that. 3, 1, 4, 2, 2, 1, 1, 1, 7, 7, 1, 1, 1, 2, 2, 4, 1, 3, 15, end. So to compute those numbers, you need to be clever. The computer is unable to calculate them. Now, looking at those numbers, I have discovered, as I have explained it to you, hundreds of theorems. First theorem that I have discovered maybe 10 years ago, looking at this and different similar numbers. Even today, I have some doubts whether I have proved it or not. Because in my proof, I have proved it that it is generically true with some exceptions. And later, my students have proved that in the exceptional cases, it is true too. So today, the theorem is known to be correct. But I have to attribute it to my students rather than to myself. So I have conjectured those, and I have proved it in most cases, but not always. The general case was the final result is due to my Italian student Francesca Aicardi at the ICTP, at the MSRI of Italy. It's called ICTP, International Center of Theoretical Physics. They consider this as physics. Theorem. All those continued fractions, as well as all those continuous fractions, are periodical by Lagrange, but more, they are palindromic. Palindromic. What is palindromic? A palindrome is a sequence, a sentence, which can be read back, and you obtain the same sentence. Look, if you it here, 3, 1, 4, 2, 3, 1, 4, 2, it's a symmetry. It means that AK equals to AJ for the sum which is fixed. I'm not writing the numbering of this K, it depends on the numbering. It's a symmetry, you know. The number 15 here is only once. Yeah. However, it's a period. It's periodic. There is 15 here too, at the end of the preceding period. So it's an infinite periodical sequence, and it is palindromic. The infinite periodical system is periodic. The finite one is locally periodic, but locally palindromic. Yeah, but you understand. I hope you understand what I mean. Okay, so that's the theorem of Aicardi. Those continued fractions are always palindromic. Those are palindromic too. However, but according to the Lagrange theorem, it is wrong for the general case of irrational quadratic numbers, because whatever be a periodic sequence, there exists a quadratic irrational number for which it is a period. However, it cannot be reduced neither to this case nor to this case. Those two cases are different from the general case. While the periods, the frequencies of elements of the periods are the same. And however, the sequence to be periodic, it's a very, very particular property. Given a sequence, to know whether this sequence is a period of some irrational number of this kind or of this kind. I do not know the solution of this. I know this palindromy is not the only restriction. There should be, by the entropy consideration, an infinitely more restrictions. And I shall explain you why there should be an infinite number of other restrictions now. Now, experiments. Computing the periods, I obtained the following answers. So this is the plane PQ. In fact, the answer period, which is put here, is the function even in P. If you change the sign of P, it's rather easy to see that it is not changing. Also, you have to take into account the following fact. The square quadratic equation has two rules. The periods are the same, and the lengths of the period are the same. Now, the length of the periods, so you see here, this table corresponds to P from 0 to 16, downstairs written, and Q from 4 to -4 to -32. -4 here. That's the beginning. This part are very small values of P and Q here. And the double lines here are the spheres P square plus Q square more or equal R square. The next problem I was doing is to compute the average. Which depends only on R. It's the arithmetical mean of the period's length along this disk. Of course, Q might be also negative, which is completely different. And I have computed this too. Q here, those are negative Q. The axis is minus Q. But for positive Q, the situation is similar. Here, however, you have a void part in the plane PQ, like here too. You have a void part. And this void part is a case of complex roots. To calculate the continuous fraction, you need the number to be real. So here you have complex roots, here real. And the period lengths, you see, are not so large. However, they are growing. There exist arbitrarily large values. 16 here for Q equal 30. You have already 16. Well, observation. This mean as a function of R. No, I put it here. R, and here the mean. 4, 8, 12, 16. Those numbers exist by my students at San Francisco who had computed it using the computer till R1000. But at the beginning it's like that. 0.66, 160, 245, 317. If you look at those numbers, you have 0.66, 160, 245, and 317. You have discovered the first theorem. It's a linear function. It's a wrong theorem. My San Francisco students have discovered that if you continue till r of order 1000, you get the following asymptotics. Asymptotics, well, it's an experimental fact. It's not proportional to r. Here it is a linear function. It is not. Yeah. It's like the Legendre discovery, you know. It's not one. It's very similar to one. You know, I know all the tables till the 1000. It's almost a straight line, but it's not exactly straight. So that's why I'm discussing those things, because there are a lot of problems, understandable. Well, now one more remark. This table you have some growth rate with r. When you are far from the origin is here, and when you are far from the origin, the periods are mostly larger. Sometimes there are even zero. It means that the roots are rational. It happens. However, the growth rate is not uniform. In fact, it depends on the direction in which you go from the origin. Namely, if you go far in the direction, if your averaging is made in the direction where p is bounded by q is large, it's growing slower. Looking at the table, you are able to see it. In fact, it is growing like square root of r. The mean, yeah, and in other directions, like r, or maybe r power alpha, where alpha is almost 1. Now, trying to understand the reason, I have formulated the following conjecture. Looking at this table, I have observed that the vertical lines are the same, all the vertical lines. Almost all. There are two columns in this table which are different. All the others are identical to them. Look, you see here the zero column. 0, 0, 1, 2, 4, 2. Those are the lengths of the periods of square roots of q. Yeah. However, in the next line, you have 2, 1, 2, 4, 2, 0, 1, 2, 2, and here you have the same. Only if you take this column and the next column, you have to shift it. They are shifted. And this is very easy to understand, because if you shift x in this equation by 1, yeah, you are changing q accordingly. But you are not changing the continuous fraction period. If you add 1 to x, the period remains the same. So it should be like that. Yeah. And because of that, I was thinking that the square root of the term discriminant is an important quantity. It is a boundary line here between the real, whether it is positive or negative. Yeah, but however, if it is a square of an integer, t is 0, the period, because it is a rational number. And so the curves where it is a constant are orbits of this motion, which is sending the period to itself. And hence, along such a parabola, the period is constant. And hence, I can guess that the period should behave like this square root. Maybe constant and maybe something to add. You have to compare this period length and this square root. That's the next experience. Now, if you are going far in the direction of q, fixing p, q being very negative, like in this table, yeah, it will be square root of q, this number. If q is of order large R, it would be square root of large R, as I have observed for the means. However, if you are going in the other direction, where p is of same order, it would be of the order of p of order R, so it is R. So in all the other direction, it is growing like R, this number. And in this vertical direction, it is growing by square root of R. It's OK. And so you can compare those two numbers. Well, my time is over. And I have some more things to show. Well, look. First, how to explain it? First, I wish to explain this table. This the same plane, PQ. However, the numbers are not the lengths of the periods, but are the sums of the elements of the period. The statistics of the elements is that of Gauss-Kuzmin. It doesn't depend on the length. However, the sum is different. And one can think that it will be proportional to the length multiplied by the average length in the Gauss-Kuzmin statistics. However, as I have explained it to you, in the Gauss-Kuzmin statistics, the probability of the A of some value of A is declining like 1 over A squared. It means that if you wish to compute the average value of A, you have to compute the series, the moment, which is a harmonic series. It diverges. And hence, the expectation of A in the Gauss-Kuzmin statistics is infinity. However, in the finite case of periodic objects, it's impossible. So it's not the product of infinity by the length. It's something different. So it's a different statistics. And I have studied this statistics just computing those periods. And then today the result is that this sum is, the today result that this sum of elements, I denoted E, and I take the average along the disk, like in other cases. Yes, and it is growing like 1.5 of R. The period length is the period length here. I was explaining that it is growing like R slightly smaller than R, degree smaller than 1. Yeah, but I think that it means that the ratio, which is the mean element of the continued fraction, is growing approximately like the logarithm of R. I think that, in fact, it is the approximation to R divided by logarithm of R. When R was till 1,000, you cannot distinguish it from R power slightly smaller than 1. And then perhaps it means that you have the R growing of the sum of the elements and R divided by logarithm for their number, and hence logarithm for the element itself. Some confirmation for this is the following result. I have computed the continuous fractions for rational numbers, the lengths. That's a table of the lengths for the continuous fractions, u divided by v, the beginning of this table. And this average, when you compute the numbers further, not only in this small domain, but further, show that this period is growing, this length is growing logarithmically. The formula, here's the formula of Gauss is here. I was aware that it is somewhere. It's on this table, yeah, you know, at the base. At the end, the base 2 logarithm of 1 plus 1 divided by k, a, k, and k plus 2. That's the Gauss formula. The integral of the invariant measure of the Gauss mapping along the interval corresponding to the value of a equal k. That's the probability. Yeah, but the sum of those elements is linearly growing with the denominator with the coefficients 1 over 2 in the mean. And that's the sum. And the number, the length, as a logarithm. Those are the experimental facts that I was trying to show you. And then, oh, but I have 1 more minute. Huh? It's okay? Well, then I would like to show you some theorem. I was explaining that looking at those results, I have discovered hundreds of theorems. A dozen will be shown now. Now, those are theorems. There are some special continued fractions for which I was able to calculate explicitly the fraction period. Yeah, and then, for instance, square root of a square minus 1. my tables of all the periods of all square roots provide, for instance, for this series, very special case. That's t equal 2. And the period is 1 and 2a minus 2. You can write, well, say, let a be 2, square root of 3. Square root of 3, the period is 1 and 2, 4 minus 2, 2, 1, 2. And of course, it's greater than 1. And then it's for all the series of square roots of 3, 8, 15, and so on for a in integer. But then you have other series which are written here. And I know dozens of other series for which you can explicitly present nice results. Oops. Now I am showing you the lists of the periods for the square roots of rational numbers. You know, P on the upper line, Q in the column, and in the intersection PQ is written the period of the continued fraction for the square root. It's also a symmetric table. Those are elements of the fraction, not the lengths of the period, just the elements. So you see here where P is 3 and Q is 1, it's square root of 3, and it is written 1, 2. Just what is here. Yeah, but others, and I'm showing this to have some impression what palindromy means. The palindrome, all those, you know, sometimes long, sometimes short, but they all are palindromic. Yeah. And now, last words. I have explained to you the lengths of the continued fractions for those examples. However, the averaging along this disk is not the only way to average. Namely, I shall report now two other ways. Example. Consider the group SL2Z of matrices of order 2 with integer elements. Then the characteristic equation and hence in my tables, in the line where P is 1, when Q is 1, contains the information on, however, if you fix the disk, the ball, of radius square root of m, there will be a finite number of group elements, there will be a finite number of periods, and you can take the average along them. And it's completely different from the average along. Of course, it's a particular case of this problem, but the weights given to give different values of P and Q are completely different. Q is 1, and P have some statistics in those disks, depending on M. which is not uniform at all, which is not trivial at all, which is not easy to calculate at all. And I have calculated it. And I shall provide you the answer. And the second answer is to take the semigroup. The endomorphisms of Z square. It means simply arbitrary matrices whose determinant is arbitrary, with integer elements the same, and the same problem. Now I'm reporting you the answer. For this case, the answer M 4, 8, 12, 16. Average 016, 037, 053, 065. Graph. Zero 2, 0 4, 0 6, here 0 and 7, next, 5 3 next, and 6 5 here. Conclusion. It's the average is growing like m divided by 25. The constant is 25 in this case for those names. However, I am a physicist. I have to observe, together with such plausible mathematical arguments, real physical reasoning, which are not proofs, but which provide some ideas on the dimensions, theory, and so on. And they provide the following answer. It should be, in fact, the true answer of order m power 1 over 2, square root of m. Now, if you look at the, it depends on the statistics of this sum of the and of the too many information, no time. Why it is m power 1 over 2, I have no time to explain you. Now, the second case, SL. Answer. It's not growing. At the beginning, it is growing, but it is growing to 2, very slowly, logarithmically slowly approaching the value 2. And it depends on the following statements, which will be my really last words. It depends on the following number theory problem, for which I was really astonished not to find any word on it in number theory books or in the, how it's called, constructive mathematics. That's a name, concrete mathematics. Concrete mathematics book in California, you know, that's con from continuous and crete from discrete, by Donald Knuth. That's the following problem. Consider a number p, an integer p, and the number of its divisors. Question, what's the growth rate of the number of divisors? This result is based on some estimation in this problem. Now, if the number is 1, what's the number of divisors? Integer divisors of 1. 1. If the number is 2, 2. If the number is 3, by induction, as Landau was claiming, it would be 3. No, what's the number of divisor of 3? Huh? 2, thank you. 4. What's the number of integer divisors of 4? Natural, of course, positive. Huh? 3, great, 5, 2, 6. Oh, many. Many. 4, of course. 4, 24. I know, 8. And 120, 16. You can compute it. Now, they are irregular because for prime numbers they are always 2. And sometimes they are very large. So they are oscillating. However, you can consider the averaged asymptotics. You take the sum of the values, you divide by the number of experiences, and you get the mean number, the Cesaro asymptotics. D of 1 plus D of p divided by p. That's the D averaged of p. Then there is a theorem that I have discovered because I have been in a hospital and I have a lot of time. I have computed this for p till 1000. And then this graph was evident. Natural logarithm of p. And then I discovered that the first perhaps who have discovered this result have been Dirichlet. There is a letter of Dirichlet to maybe Gauss or someone when he is mentioning that he is aware of this. However, I have discovered it completely independently. Now the problem is, what are the deviations? You know, to study the deviations, I proposed the following numbers. D bar is maximum, D bar of p is maximum of D of k for k smaller or equal to p. Well, p, D bar for p equals 6, it is evidently 4. For p equal 12, it is in fact 6. In fact, between 6 and 12, it is always 4. All the jumps will be mentioned. Next jump is 24, providing 8. Next jump is 36, providing 9. 48, providing 10. 60, providing 12. 120, providing 16. 180, provided 18. 240, providing 20. And I suppose that 720 is providing 30. But this is, I have not checked exactly. Or maybe 31 or 29. Okay, now look, conjectures. First, conjecture. If the number is a factorial, 6, 24, 120, and also this one, then the value of D is extremal. The factorial have the maximum possible number of divisors, more than any other preceding number. I am unable to prove it. That's a conjecture. D bar of m factorial is conjecturally equal to D of m factorial. A weaker conjecture, D bar of m factorial divided by D of m factorial tends to 0, to 1, sorry, for m tending to infinity. It's a number theoretical problem. I wish it to be solved. I don't know. Next conjecture, that the asymptotics of D bar is like that. That's D bar of p divided by p any power alpha is tending to 0 whenever alpha is positive, tending for p tending to infinity. And the asymptotics of this, you know, the mean value is logarithm of p. And for the other cases, it seems that it is much larger. However, I have proved this. It's a theorem for alpha greater than 1 over 3. I suppose it's always true. I think it is logarithmical, but I cannot prove it. It's really a challenge, and that is the reason why I'm explaining it. It's a nice challenge for number theorists, algebra, and so on. But I am formulating the lemma on which it was based in my proof, this 1 over 3. It was based on a theorem that I have proved 20 years ago, and which is nice itself, and which is a real theorem. Consider a convex polygon, for instance. There are theorems for any dimension, but polygon in R2, such that the vertices are integer points. And the area is S. What is the maximal possible number of vertices? The number of vertices is at most a Wald constant, I have forgotten it, S power 1 over 3. There is an example when it is indeed 1 over 3, and this is the example is a parabola. X equal y squared. If you count here the integer points, you make the calculation, it's cubical. Because, you know, if this height is y, then x is y squared, and then this area is y cubed. And the number of integer points is 4y. And this is the extremal case. That's the theorem. And this theorem is implying this. And this theorem is implying, where is it? That the limit is, I have destroyed it, that the limit is 2 for this case. For the case of the group SL, the limit is 2. It's implied by this theorem in convex geometry of numbers. Thanks for your attention.